Today, I want to talk to you guys about scaling full-stack applications. My name is Wilker. I am natural from Recife in Brazil, and I have been working with Clojure for some time. I work at Nubank. If you guys don't know Nubank, Nubank is a financial institution, a fintech from Brazil. And one of the values that we have is that we want our customers to love us fanatically. And one of the ways we try to accomplish that is by giving very good customer support for our customers. So to do the customer support, the customer reps have to use some back office software, right? And this software at Nubank is called Shuffle, and that's the project I have been working on, and that's what I'm going to talk about to you today. So this is Shuffle. This is like the entry screen of it when people start logging. This is a chat screen when they are responding chats to the customer. And this is what we call a person deck. We're going to focus a lot on this part today because we're going to talk a lot about data fetching. So just some numbers to give you some sense of the size of this project. It has over 15,000 commits, over 120 contributors, more than 75,000 lines of Clojure script, and it gets deployed at least 3 or 4 times a day. So it's high churn, everyone is using it all the time and deploying all the time, so it's kind of critical service there. So the first problem is, where is my data? When you're trying to write code like this, if in Nubank we have microservice architecture. So here, this display is that all the information we know about the customer. So every squad on Nubank might touch this and try to add things here. And this data can come from a many variety of services. So to load this data, we start from a customer ID. That usually comes on the URL, and that's the first information we have available to us. With this, we can load things like the person information, or the phone numbers, or the boletos. And you might wonder, what is a boleto? A boleto is this. This is how Brazilian people pay their bills. But yeah, continuing. But customer ID is not enough to access all the data. For example, to get card information, it's not associated with the customer ID, but it's associated with the account ID. So you actually have to fetch the account ID for somewhere else first, and then you get that. Same for shipping information, and same for account information. And actually, the account information and the cards are on orange because they are actually the same endpoint. So you don't want each component to be requesting the data, because otherwise you have duplicated requests. So it's not good. There are even other more strange relationships here, and I just highlight to you the purchase widget and the chargebacks widget. And the purchase widget has to display the chargeback status if that purchase has a chargeback. But customers usually don't have a lot of chargebacks, so it's actually faster to load all the chargebacks at first and just associate it back. But then it's more things you have to coordinate. And those are just a few examples. There are a lot of weird things that need to happen if you want to get an efficient data fetching to display all this screen. So, and also there is the problem that, look at the number of requests at some point. This is not true anymore, but you see that as people add stuff, it's growing, growing, growing infinitely. So some problems with the architecture in the way it has been done before. You have to write a lot of complex code just to coordinate this data fetching. We have imperative loads with callbacks that create brittle dependencies. You want to add something, and you say, OK, I want to add some data. What's my requirement? And then you have to manually scan all the code to find, oh, who is requesting that? Can I leverage this? It's a lot of pain. Also, because the code that fetches the data is not collocated with the code that renders the components, when you try to remove a component, you have to manually go around and see, oh, can I remove this data fetching? Is anybody else using that? And sometimes people go wrong and bugs happen. And then it generates a large number of requests done on the client side. So if we're not doing that, what can we do? And then I'm going to talk about declarative data requests. And one heads up, I have a lot of things that I'd like to show you guys, so it might go a bit fast. And most of the things that I'm going to show you, the libraries, they're all open source. You can use them today. So to get you in the sense and the idea of how we are doing this processing, because it's quite a different thing, I want you to think about select keys. And I want you to think of select keys in this framing. The left argument is the context, that is, the information you have. and the right side is, the context, and the right side is the request. That's the information you want. So for example, if I give you this map and say, oh, I have a map with first name Wilker, last name Silva, and I want the first name. Okay, you read on your context and you get that data. But names have this quite interesting property because they have semantic meaning. So I'm going to do a different request here that select keys can't answer, but I'm pretty sure everyone here in this room can. That is full name. Okay? In your heads, you know how to solve this, right? You know how to get this information. That will be this. And that's what we're looking for here. We're looking for a system where we can just describe what data I have now and describe what data I want, and it should be able to figure it out. And the next question is how we implement that. Of course, there are many ways we can do it, but I'll show you the one we are doing. And this idea comes with this idea of resolvers. They are a bit different from GraphQL resolvers, if you heard about those. In our case, resolvers, they are the edges of your graph. If you think of your data as a graph, the resolvers are the edges. So a resolver is composed from a symbol that identifies the resolver, like a var that you do, just an identification. A resolver contains an input, and the input says, this is the data I need to run. So I require a first name and last name. And the output that describes what gets out. And one thing important in this system is everything is labeled. There are no position of things, so no slots. And at the end, you have a resolve function. That's the lambda that actually does the computation and converts one thing into the next. So with that, let's go to our first demo. And I'm going to come here. OK. Let me clean this up. So here is an actual resolver. This is how you actually write it. This has the same things, just some namespaces around. And here is a function that I'm calling to try this out. So let's see if I get this context. I have first name and last name. I ask nothing, I get nothing. If I ask for the first name, then I get the first name. Now, if I ask for full name, then it can run the resolver and get me the computation out. Cool. So what else can we do with resolvers? That was a very simple case. The next very common thing to do is expand data. Before we compute the data, we got some information transform. Another very common thing is to request data. So let's say we have this email database. This email database contains, it's just a map that goes from email and first and last name. So now let's create a resolver that get an email input and output first and last name. So the implementation is just a get. But this could be anything, right? Could be your Datomic database. It could be a web service. Doesn't matter. And then we do that. So again, if we start with the context of email, I can ask for the email here. And I get the email out. I can ask for the first name, because it's going to run the resolver and get that. And if I can get first and last name, oh, that should mean that I should also be able to get the full name, right? And fair enough, you can get the full name. And the way the library does this is it has an internal structure. So when you ask for something, it runs this function. So in this case, I'm telling the engine, hey, I have an email. I want a full name. How do I get there? And the engine is going to traverse an internal graph and give you the possibilities that you can do to run. And internally, it runs and does it automatically for you. And I hope you can see how this can start to compose. Because that's all about. This is about composing. It will traverse you don't need to know the middle terms, right? I start an email and full name. I don't have to know about first and last name. So to the next. So far have been just flat things. So let's see how we can go about processing lists and other things. Remember the select syntax that Rich showed yesterday? Same thing here. Same thing as the Datomic post syntax or the others you know. So here we are expressing a shape. We're telling, oh, this resolver, it outputs an all email key, and inside of it we'll have email keys. And the implementation is just it converts that hash map and extract the email. So if I ask for just all emails, what I get is this. I get a list of emails. But hey, I can make a selection here. And I say, OK, but what I really want is the full name of everybody. And Fair enough, you get the full name for everybody. It does the same processing, right? Starts with the email, navigates, and does the thing. One more piece of syntax that I have to introduce you now is entity joins. This is a join for all emails, and that's fine. And we have been playing around using this context map, but in the real deal, you don't have this available directly to you. You only have the query. And starting queries from a single attribute for email on this example, or for a customer ID, or whatever ID you have, is a very common operation. So we have this lookup half syntax that is pretty much like the datomic halves. And when you query for those, this is a vector instead of a keyword, what you get is a map that has that same thing. It's pretty much converting the parentheses. And what this enables us to do is at query time, I can provide a piece of information, and then I can request information out of that. So I can provide this piece of information, that's the email, and ask for the full name, and you get the full name. Okay? Okay, so let's move on for the next example. This resolver will give us the answer to the word and everything, as everybody here knows is 42. And let's run this guy. And one interesting piece about this guy, and the last resolver also has this property, is that those resolvers don't have an input. They only have output. And I call those guys global resolvers, but really, we are treating it as a graph. Graph has no roots. If something doesn't have a dependency, you should be able to ask for it anywhere. It's different from what GraphQL does, that there's the specific root types. We don't have root types. And then you can ask for this anywhere. So doesn't matter how far or which part of the graph you are. And this is an interesting property. Okay, now one more thing. Now I'm going to show you something that might be counterintuitive at first. Let's see, now we have another relationship now. And this relationship will be from hosts to the host description. So we can get the email host. So first let's write a resolver that can extract the email domain from an email. So if you just ask for, provide an email and ask for the domain, we get the domain. And then we write another resolver to get the host. And this is what I think most people would start with. That's like, okay, a host is a relationship of the email, so let's make a nesting to that relationship, and then we have this. But I'll encourage you to do something different, because flat structures are usually simpler and better to deal than nested structures. So if you're making a 2-1 relationship with something that doesn't have shared keys, it's all good to flatten it out. And that's actually better because then the engine can do more for you on flat levels. It can navigate more steps automatically for you. So if you do that here, and come here, I'll update this thing. And so now from the email, I can ask for the host name. And as you add up, this gets really useful. When your system is growing and all these 2-1 relationships live together, it gives you a lot of reach. You just provide a tiny piece of data, and you ask something that's very far away, and the engine can navigate all of it for you. Okay. And now, when you think about this flattening thing, you might be thinking, okay, this flat seems good because of the expansion and stuff, but UIs are trees, and sometimes you want to have a structure. So let's say you want to write a component that's a host visualization. And then you want to join because you just want to provide the map with that stuff. You don't want to mix with what was before there. And what you really want to do is you want to do a join, but you want to do just to break the thing, right? Let me get you an example here. Let's write email. And I want to have a join to something that will have the same data there. If I just do it like this, the engine say, oh, not found. I don't know what to do with that. But there is a special namespace. And if you use this special namespace, and this is just a regular closure keyword, by the way, this is a valid closure keyword. If you use this greater than namespace, then you are doing what you call a placeholder node. So it's like an edge on your graph. You are reshaping your output, but you are remaining on the same context. So you can see the email was this here, and the email is this there. So I could ask for my host domain and host name here, like I could do on the parent, And then this allows your UI to decide how he wants the shape. Instead of us trying to figure out ahead of time, this gives the flexibility to the query, to whoever is asking for the query to define how he wants to shape it in this sense. And okay, that was it for our first demo. And by the way, we have been a lot of time talking about this query language as the atomic pool syntax, Omnext query language, Fulcro query language. We got tired of it, so we decided to name it, and now it's called EQL. That stands for EDN query language. We are starting to write the specification. We have actual closure specs for it, including generators, so you can generate random queries and just see what happens, if you like. And the specification, the text formal specification, we're going to be writing soon after this event, and I have more time. Okay, and now let's see EQL in action. Now I want to show you some situations that might not be obvious because they're not used to this, but I think are interesting cases to use when you are building UIs. For example, one first example is UI predicates. This button that I highlighted here, it should only show up in a specific situation. Only if the customer can anticipate that purchase, this button should show up. And in my experience, what people do is that, okay, what's that condition? Oh, I need to look at this and that. So they put the data on the client side and process that on the client side. But really, the client doesn't care about how this is implemented. Instead of doing that, just make a label for it. So you can call, give it a new name. We name this operation, we name this predicate. And then we can implement it as a resolver. So you can say, okay, to know if I can anticipate a purchase, I need the purchase status and the purchase source. And then it outputs the can anticipate. Because now the UI can just ask if they can anticipate, and that's it. The same thing can be done for access predicates. This button is similar to the previous one, but this one depends if the user has enough access to do that. Again, we can write as a resolver, and this guy fits on that global resolver definition. It doesn't have an input. So any component could ask for this information anytime. And these things I'm showing you are about freeing you for context-dependent things. You always talk about the attributes directly. It's like this playing field of attributes for everybody. We can do the same thing for enumerables. So if you have an enumerable, name it, expose it through a resolver, then you can ask it wherever you want. Now let's go to one of the start gets a little bit more advanced. That's about request caching. Remember that I told you before about the chargeback relationship. So let's look at this query. This query is starting providing a customer ID at the ident at first level. And from that customer, we are asking for all the purchases that that customer made. And for each purchase, we are asking for the merchant name and the chargeback status. And when you run that, we have this tool here. We might not be able to read, but that's fine. This is a tracer tool that gives you details about how each attribute was processed, what resolver it called, how much time it took. This enables you to debug and understand what's happening under the hood. And as you can see here, we got some time for the customer, some time to load the purchases, and then the chargeback status was only loaded once. You only see one bar because it loads all the customer chargebacks and associated the information automatically. Now, what happens if I add the customer chargebacks to this query? Because now, the chargeback status and this customer chargeback actually hit the same place. They are both loading the customer chargebacks for this customer. And we actually get faster because now it can do the purchase and the chargebacks in parallel. And if you look at the purchase numbers, the bars only end when the chargebacks end because it knew it was depending on that, so it was waiting for it. And after that information was available, it uses and mounts the output for you. Backtracking. As I told you, this system, as you add resolvers, you might have multiple paths to get to a single attribute. And when that happens, if it tries a path and a path fails, it can try the other path. So in this case, this example, we're trying to load the account ID for a customer from a reward service, but this customer doesn't have rewards, so he can't get their account from that. So it tries the other path, and the other path works. So let's talk a little bit about some properties of this system. First, it's a declarative system, declarative definition of relationships between attributes. There are no types, no boxes whatsoever, only plain attributes all the way. It supports multipaths. You can have multiple ways to do that, and the engine will try to figure out the best way to handle for you. It does automatic orchestration. It parallelizes automatically for you. You don't have to write a single line of code to make it parallel. You just write your resolvers, and the engine can figure out, oh, okay, this depends on this, and it can automatically orchestrate the request for you. It encourages the domain logic to be kept out of client code, because it gets so easy to write these resolvers that people prefer to write them on the server side. And then you have this available to any client. If you have multiple clients, all of them will be seeing the same view and have the same stuff available. It's resilient because it can backtrack and try other paths, try to figure the best way for you. And it's explorable. We don't see it yet, but we're going to see it a bit later. And this library is called Petal. It's a library that I've been maintaining for the past 2 years, pretty much. It was just something that I copied from project to project. Then it got to be a library, and you can use that today. Now I'm going to talk to you guys about how we can use this query language and syntax to build actual user interfaces. That's what the talk was about, right? So to get there, first I want to show you how you can visualize your interface only in terms of attributes. And you can do that if you look at a widget like this. When I look at this, I try to find what are the variables here. And then you just start labeling each variable. For example, here is a customer name. Here is a customer email. Here is a customer date of birth, customer ID, prospect ID. And that's fine. You can mix multiple namespaces in the same map. That's totally OK. More examples here, some car data. Here for the purchases, you can have the customer purchases and then each merchant data. So you can label every piece of variable in your UI as a single keyword. So it gets you simple to reason about, simple to implement. You don't have to do those crazy things like trying to look it up because it goes through 5 different processes and you don't understand how it got there. And from that, I'd like to talk to you about the React formula. Because this is what got Clojure excited about React when it was released, right? Because, oh, finally, we can do something functional. We can write functional UIs. My view is just a function of my data, and that's it. And this formula is pretty nice. I like it a lot, because it makes simple to reason about your app. If your app is a variation only of your app state, how many places you have to look when you want to understand your app? Just one. But at the moment you do set state, oh, just to show that modal on or off, you've broken the property. The same thing for reagent atoms, local reagent atoms. If you just use one global reagent atom, all good. But if you start using local reagent atoms, you are getting to the same place, to the same problem. So I guess ask you guys to think about that when you're trying to design your things. It's trivial to create. It's just a map. So if you want to reflect the state of your app, just recreate the map. You're done. You can do historic analysis. You can do processing on this. If you look at how your data varies across during your program workflow, you can try to automate and get some interesting things out of it. Also, we like pure functions, right? So we should like pure components as well. If the component needs to look at the props and the state, then it's looking to 2 things. It's not pure anymore. If it looks only at the props, it's completely pure. And today, who here knows what Fulcro is? Oh, good. Nice. I was talking to people, everybody didn't know. Nobody knows that. But yeah, Fulcro today is the library that I think better suits for this graph thing. Petal was written for Omnext and Fulcro in the time, but although it's not mandatory, they are very good combination. So let's take a look at what a Fulcro component looks like. Today, we're going to look about just one item of a bill, like this. And this is what it looks like. you see there is a defsc that defines the component. We give the name. There will be like the component class name. And it receives this and props. And this first part, the ident, is where we create, like, we tell where the address of this component in some sense. Remember, we can do queries starting from a single property. So the ident of this guy is BUID with the ID, whatever it is. So it automatically works as an initial thing if you want to load more data about this component. If you provide the BUID, you can probably get most of the data about the bill. And on the query, you specify exactly what attributes you need to render that component. So you can see here on the query, like this, you can map them out. And the ident also serves to tell you on your local database where the data for this component will be. Because there will be a map, and if you follow the ident, it will be BUID and ID, there you have a map with your data. The database gets automatically normalized to you. That's a very nice feature over time. And I think this fits very well with the React formula, because you look at the top part, that's the data description. You look at the function part, that's your implementation. And in the end, you get your view. Now, I want to show you a bit about how we compose components in the system. So first, let's say now I'm writing the bills list. So the bills list has its own things it needs. But it says, OK, I'm going to list the account bills. So this component knows what are the set of the bills that I'm going to list. It will be the bills about this account. And the subcomponent tells the details. So this keeps those things separated. If the detail needs more data, it doesn't have to change the parent. You just change the children, and you get it. A little bit more about this composition thing. Let's see this on the deck. I show you two different queries, of course, very shortened for these two components. And I keep both green, because both are on the same context. Like this customer ID will be equal for both. But each is asking a different subset of what a customer ID can provide. When you do a join to all cards, then we change in contexts. So it's different. But then we need something on top of all of that to put everything of this together. And that's where those placeholder nodes you saw before came to hand. Because then for each entry, I can have a different placeholder that matches that component. And this way, I can have as many as I want. And in the end, that's what your full query looks like. All components composition all the way from top to down. OK, let's talk a little bit about what it looks like to develop in this environment. First, I want to introduce you to Workspaces. If you guys, anybody have ever seen Workspaces? Cool. So we just released 1.0 last week, so try it out if not. And Workspaces, for those who don't know, is like a dev cards environment, but it's more optionated about how you plan on your UI. Instead of having namespaces and cards as an option, what you have is a bunch of workspaces like this. You can have multiple at once. Each workspace goes in a tab. And inside of the workspace, you have the cards. And this is a grid, so you can resize and reposition the cards as you see fit. Another interesting property about our development workflow is that because we have all these namespaced keywords, when we are developing the widgets, we don't ever have to touch the server. We can just use test check generators to generate and populate the data. So in this example, I just restarting the component, it's generating new data every time. So we never have to write fixtures. And that's a lot of time saving when you are trying to develop stuff. So we also have this tool called FookRespect. That is a development tool for Fulcro. It runs as a Chrome extension, so you can see it side by side while you're developing. So you can see the database and try to track down the thing that I told you, like go on purchase ID, get the ID, you are on the map. All the data for that purchase is there. There is no question, like you don't have to keep looking up. It's very obvious where the data for that component is. We also have this transactions panel that would be like a dispatch from Reframe. And those are the guys that mutate your local app state. So you can see here, we can even give you diffs. So you run a transaction, and this can tell you exactly what changed in your database. So you know what's going on, and it helps you improve debugging. We also have this network tab, where it shows all the network requests that were made by the FookRespect app. And you can even have that tracer feature integrated right here. So just keep working, and you can see on details what's going on and what queries meant. Also, this is a bit about the exploratory capabilities. We have a query runner built in on the FookRespect as well. And if you are using Petal with Connect, that's the feature I'm showing you, you can get autocomplete. Connect is introspectable, like GraphQL. It can expose its index, and tools can use the index to provide contextual autocomplete for you. So you can just try it out and see what's available. We can also run tests integrated on Workspaces. These are two examples running one full namespace and one single test, but you also support running your full suite at once. So you choose the granularity that makes sense for whatever you are doing. Okay, let's talk about some declarative data tricks. One of them is lazy properties, because not everything has to be loaded at start. So you can mark some part of your query as lazy. And then when you do that, it doesn't do anything. This is a local function for us. But because your query is EDN, you can pre-process it before sending to the server. So when I call, I can decide, oh, if I don't want if I want to do an initial load, just kill every property that's marked as lazy, and that's it. Just data, do wherever you want. We can have incremental loads. For example, again, on that purchase details. If we go to load that from the beginning, from just the purchase ID, it can take this time. And if you look on the scale, that's almost 2 seconds. And you can see that there are 5 requests because of the blue lines, but one of them is a perpetrator that's getting way more time than the others. And the thing is, when we loaded the purchase list, we already had that data. We already paid the price for this. So this is a waste of time to request that again. So what you can do is send the purchase ID and also send all the data that I already have. So when the server looks at it, it already has a pre-filled purchase and only has to work on the fields that are missing. And then you can drop the time to like this. Now 100 milliseconds, and now it's tolerable. For monitoring, Petal is extensible through plugins. So in this case, you just write a plugin that runs around resolvers, computer time, and log into a Prometheus, and you can display on Grafana and follow it, see what's going on. For testing, we can use the generative data again to test. Just generate a bunch of data, render, and see if the component doesn't crash. This can get a lot of minor mistakes that people make, and so prevent them from happening. There are other stats, but I'm not going to talk about them today. And now I have one more demo for you guys. And so far, we have been playing around on this interface here, but you can do on a browser as well. So if I come here, you can see we have the data available that we provided, so the answer of everything, or I can ask for all emails. And if I do a join here, see, the autocomplete is contextual. Now I can have an email, I can have first name, I can have phone name, I can have domain name, or anything I want. And that works. You see the tracer here. But let's spice it out. And that's now the time that I hope the internet works. So resolvers, like I told you, they are just maps. And you can expose resolvers as a library. So in this example, I implemented some of the YouTube API using this as resolvers. So when we import the YouTube API here, what you're saying is that, please give me all the names from YouTube. And now we can ask things like, oh, I want the GitHub, the YouTube username for Closure TV. And I want the latest videos. And for each latest video, I want the video title. And there we go. Probably some of the yesterday videos or right now. OK, cool. But let's add more stuff. Let's add the SpaceX API here. So I wrote some of that. Those are very incomplete, by the way. But you guys are invited to add more resolvers and make it complete if you like. So let's add the SpaceX API here. And from the SpaceX API, I can ask for the latest launch. And for the latest launch, I want the flight number, and I want the mission name, and I also want the video link. And then you ask for that, okay. But now an interesting thing, the video link is a YouTube video URL. Huh, okay. So do I have that available? Let's start here. If I can provide a video YouTube URL. Oops, sorry, I missed my syntax here, okay. And I can copy this out. So let's provide a video URL to this guy. And now I can get the video title again, or something like that. And you can see the request to YouTube was only done once. Because again, caching, local request caching. The engine guarantees to you, you're not going to call the same resolver, the same put twice in the same query, ever. But okay, but I can't ask for the YouTube stuff here, right? No YouTube. Because the engine doesn't know there is a connection between the SpaceX video link and the YouTube link. But we can teach it to him. We can just say, hey, let me define an alias, and a SpaceX video link can be converted to a YouTube video URL. And once we do that, okay, now all the YouTube data is here. So I can ask for the video title right here, just to remove noise. And there you go, you got that. But why stop at the video stuff? I want the related videos as well, because I want to show more interesting stuff about that. Or also, why not some channel information? I want the latest videos from the channel of this video. So you can get the video title again. And there you go. All the data is here. Okay, are you done on that? No, let's add one more data structure. But this time it will be different. This time I have this GraphQL API here, where I wrote some of my favorite SpaceX launches. It only has the SpaceX launch number, so the flight number. To import a GraphQL API, you don't have to do manual work. Petal already supports that. All you have to do is configure it. You say, oh, that's the URL. You have to prefix it with something. And okay, I have to, let me see if that is running here. If that's responding. Yeah, it does. So I run this. This is going to download the schema from the GraphQL and convert to the index of Petal. And when we do that, let me go here back. Let me start this. And now I have all the GraphQL available to me here as well. So I can get my favorite launches. And for my favorite launches, let's get the flight number. Oops, let's go down. And then you got the flight numbers you see on the GraphQL API. But again, let's connect the dots. Let's create an alias that tells that our conch Petal favorite launch is the same thing as SpaceX flight number. And once you do that, we can have things like the video title, right? Sorry. Yeah, still video title. Because then connects SpaceX, connects there, pulls that. But before I run this, I want to show you the performance characteristics. And that's a good time to also tell you that Petal runs both on Clojure and ClojureScript. So you can write your servers, your parsers both on server or client, wherever works better for you. And let's see how this is going to happen. Okay, no. Oh, did I save this? Sorry. Favorite. Oh, sorry. I have to get my flight number here. Yeah. Yep. Okay. And let's get. Okay. If you look at this waterfall now, you can see that it started requesting the GraphQL stuff. Then SpaceX API doesn't support batching, so it did 3 separated requests in parallel to get that. But the YouTube API supports batching, so it does a single request with the collected data from the previous thing. And all this orchestration is done automatically to you. So I can go back here. So my point with this talk is that composition is key. Composition is great to do these kind of things. Because when you're working at Nubank and you have all these teams working on this product, we want to be able to add and remove components at any time. We want them to be fast. And you can't count on every developer on the company doing all the best effort all the time. And what this gets us is this. The components express exactly what they need. And the API will try to fetch exactly what's needed, nothing less, nothing more. And if something gets removed from the query, it gets removed from the result as well. So you don't have this fear of, oh, if I'm removing this, I'm breaking that. No. And you can have the visibility with the tools. You can see what's going on. So you're not lost in the wild trying to understand what's going on with my API. So it helps. I'll just drop this. And I'd like to talk to you guys about some future stuff. This is a lot of effort, and very little people are working on this. But there are things we want better. Want to improve the code mirror. Right now, it doesn't support completions for mutations or parameters. So those are going to be improved. We might have generated attribute documentation. That index that you use to fetch stuff is a very rich source of information about your system. So we might have in the future automatically generated APIs, so you can see all the keys that are available, how to get to that key, what are the possible paths to get to that information you want. And again, no input for you. This we'll do once, and it's ready for everybody. Graph-to-graph communication is something that I'm really looking forward. There are some capabilities for it, but it's still very in the beginning. But I imagine if someone else already has a Petal API, we could just point to that, pull their index, and then delegate subqueries to it. And those systems could just integrate very easily. We just get the URL and you're done. Maybe streaming APIs. And one thing I get asked a lot, and I'm just going to show you something that doesn't work, because just me thinking about future code. That is, a lot of people say, OK, I'd like to use Petal, but some of my customers, they need a GraphQL API on their side. They're not going to consume EQL or EDN. So this doesn't work yet. But I brought this. This is an example from the Lacinia documentation. And Lacinia is a GraphQL provider. So I imagine in future, we could just get this Lacinia schema and map out and say, OK, this property of this type maps to that attribute. And from this information, you could just auto-generate a GraphQL API on the outside. So then you have two-way communication fully integrated on the system. And that's what I have for today. Thank you very much, people. I don't have time. Yeah. I'm over time. I can take questions now, but I'll be out here, and I'm on these channels on Slack, so feel free to hit me up. Thank you very much.